Hello, everybody. We are now beginning Unit 10. And Unit 10 is going to be all about acids and bases. So here I just have the schedule. It's a pretty short unit. It's only 4 lessons. It's today, right? We're going to talk about acid-base theories today. Like, what are they, essentially? We're going to look at reactions involving acids and bases. We'll talk about the pH scale and acid-base indicators. And we'll end the unit with a lesson on titration, which is a laboratory process that we'll talk about. Okay. This is also posted online under Unit 10 overview. Also, the standards are in that document, so definitely check that out. Today, we're going to look at acid-base theories. So really, the intention for today is just to determine what qualifies as an acid or a base. Okay? Pretty straightforward, but it's a little more complicated than just say, a real simple indicator, because there's a couple different ways that we can classify something as an acid or a base. So before we jump in here, go ahead and pause the video and try to answer these two questions. Now, these are simply just, relating to where have you heard these different words before. So what are some common acids and bases that you know of? And where have you heard the word electrolyte used before? Go ahead and pause, answer those questions. Okay, so probably the most common acid that people come up with is hydrochloric acid, right? HCl, or stomach acid, right? Maybe you said battery acid. What else are some common ones? Maybe sulfuric acid, if you've heard that term before. Or citric acid. There's a good one. There's a pretty common one, right? Citric acid, everyone's heard of. So we know about acids. Bases, probably, you might not have been able to come up with one of those. So the most common, but maybe you don't know what this is lye, which is sodium hydroxide. It is a common base, maybe not common in the sense that people even really know what it is. But good on you if you came up with a base. And then the second one here, where have you heard the word electrolyte used before? Most likely, probably in like a sports drink ad or something. Maybe on like a water bottle that says like added electrolytes. So it's definitely in marketing, right? It sounds great. Ooh, electrolytes, right? They always put it on the bottle. I think Gatorade is like replace your electrolytes, right? We'll see kind of how it's kind of silly. It is important. You do need electrolytes, but they're not as special as Gatorade would like you to think that maybe only they can get you your electrolytes back. Okay, so let's jump in and let's start talking about what these electrolytes really are. So first, I'll give you what a non-electrolyte is. So something that is not an electrolyte is a compound that will dissolve in water and form a solution, but it doesn't conduct electricity because no ions are produced, or there are no ions that dissociate into the water. So, what's an electrolyte? Well, it's a compound that, when it dissolves in water, it does form a solution that conducts electricity because it creates free-floating ions in water. Okay, now, right, Gatorade, for example, you might think, oh, what are the special ingredient, these electrolytes? Salt water. If you put salt in water, salt is an electrolyte because it breaks up into Na and Cl, right? Na plus and Cl minus. So any ionic compound dissolved in water is an electrolyte. So salt water has electrolytes in it, right? Don't drink that instead of Gatorade, right? Because it's you don't want to drink too much, right? It's also about concentration. But really, any dissolved ions in water counts as an electrolyte. Okay, so let's do a little test here. Which one of these is considered an electrolyte? Go ahead, take a look. Pause if you need to. So hopefully you noticed one of those things is not like the other, and that would be C, okay? Because I kind of just gave that one away, right? So, but let's dive into this a little more, right? Glucose and sucrose and water, all of those are covalent compounds. There's a throwback, right? Comes back. So covalent compounds, right? They don't break up when you put them in water. They dissolve, right? They will dissolve. They'll get dispersed through the water, but they don't break up like ionic compounds do. Now, choice C, table salt, right? We have sodium chloride there. It's sodium chloride when it's a pile of salt. When you put it in water, though, it dissociates into Na plus and Cl minus ions. Okay, so the only thing here that is going to create ions in water, which is what you need to do if you're an electrolyte, is table salt. Okay, and then here's a review question for you. Okay, now I'll give you a little hint. All those answers, all of those things are ionic compounds. So these are all, when you put them in water, they all are electrolytes because they're all going to make ions, and ions dissolved in water will conduct electricity. But the question is, which of the following 1 molar solutions contains the most ions? I'll give you a little hint before you try it. You're looking for which one of those has the most ions in the formula. All right, go ahead and try. Okay, so hopefully you guessed A, or came up with A, not just guessed. Because CaCl2, you're going to get 1 calcium and 2 chlorine ions for every unit of this, right? Whereas all the other answers, you only get, right, so a total of 3 ions. That's 3 ions. All right, 1 calcium, 2 chlorines. But B, C, and D, you only get 2 ions each. So you get Na and Cl, that's 2. You get KCl, that's 2. You get magnesium and oxygen. That's just 2. Okay, so the answer here is A. All right, but the key takeaway from this, right? An electrolyte is just an ionic compound dissolved in water. Because ionic compounds, when they dissolve in water, they dissociate into ions that can conduct electricity. Okay? All right. And why did I talk about electrolytes in a unit on acids and bases? Well, we're going to see that acids and bases, they're electrolytes. Okay, they dissociate in water, but they're very specific types of electrolytes. Okay, so this lesson is going to be a lot of pausing if you're doing it right. Okay, so on each one of these slides, I'd like you to pause before I go through it. Try it out yourself, because all the information is going to be on the tables I'm presenting. So go ahead and try it yourself before I go through it. I'm going to go through it relatively fast because you have the option of pausing. Okay? So pause now. Try to answer that question. I'm going to keep going. So it says, examine the properties of the Arrhenius acids in Model 1, which is this whole table here. Okay? We have Arrhenius acids and bases. List 3 properties that all Arrhenius acids have in common. Well, if you look, right, these are all the acids here. Okay, see the top, the top 6. And look, all of them taste sour. They all turn litmus paper red, and they all conduct electricity. Okay? I mean, that's everything I can get out of this table. So acids taste sour, you know that. Ever, try to eat a lemon, okay? That's the citric acid you're tasting that makes your, you make sure like your lips pucker up because it's so sour, all right? Citric acid here, right? Also, we have ascorbic acid. That's vitamin C. Okay, cool. So hopefully you notice some of those properties. Pretty straightforward question. Number 2, and again, pause before I go through it. Okay, I'm going to go through these kind of fast. Examine the chemical formulas for Arrhenius acids in Model 1. So now we're just looking at the formulas here. What feature do all the Arrhenius acid chemical formulas have in common? All right, so if you noticed, if you're looking at these acids here, maybe you noticed what's in front of all of these formulas. Yep, that hydrogen there. Okay, that's super important. Okay, what you'll notice is an Arrhenius acid always starts with hydrogen. Okay, that's key. It's a key point. So make sure you got that one. All right, so all the Arrhenius acids, which is one way to classify acids, have this hydrogen in front of the chemical formula. Okay. Number 3. Examine the properties of Arrhenius bases now. So now we're going to look at the properties of bases and list a couple properties that they have in common. Okay? And again, pause, try it yourself. If we look at our bases here, we got 4 bases down at the bottom. Also, all the bases conduct electricity. Okay, cool. But they turn litmus paper blue, all right? And they're either very bitter or they're poisonous. And the poison is also bitter, but it'll kill you, right? So we have acids are usually sour, bases are bitter and can be very poisonous. acids can be poisonous too, in a way, because if they're strong enough acids, they can be very harmful. Okay, number 4 here, examine. Now we're going to look at the chemical formulas for the bases, okay, for Arrhenius bases. What anion, ooh, there's a word. Remember, anion is negative ion. Do all the Arrhenius base chemical formulas have in common? Okay, so hopefully you paused and you noticed that all the bases, what's that OH called again? Right, they all have this OH. That's a polyatomic ion, and that's called hydroxide. Okay, so Arrhenius acids all have hydrogens. They all have hydrogens, and they're going to produce hydrogen ions in water. Arrhenius bases, they all have hydroxide ions, and they're all going to produce hydroxide ions in water. Okay, so Arrhenius acid, H plus, right? Hydrogen ions. Arrhenius bases, OH minus, hydroxide ions. Okay, and that's the key. That's how you classify an Arrhenius acid or a base. Okay, if something donates H plus, if you put something in water and it dissociates and it makes hydrogen ions, so you're going to see hydrogen at the front of the formula, it's an Arrhenius acid. You put something in water and it creates OH minus ions, hydroxide ions, that's an Arrhenius base. That's how you classify acids and bases if they're Arrhenius. Now, there's a second way to classify acids and bases. Okay, there's 2 different ways we're going to learn about. So we're going to talk about something called the Bronsted-Lowry acids and bases. Now, Regents questions usually just say, like, what is one way? They usually don't name the Bronsted-Lowry, the people that came up with this, but we're going to use their name, the proper name of it. So the only way to be able to distinguish Bronsted-Lowry acids and bases is if you have the whole reaction they're involved in. And you'll see why in a second. Because it's not just about what they have in them, it's about what they do. Okay? So again, go ahead and pause and examine these 4 reactions and try to answer these 2 questions. And please, as I go through each slide, do pause and try it first. It'll make your life easier later when you have to try to remember this stuff. It'll make it stick better. Okay? All right, so number 1 says, atoms of which element are present in all of the Bronsted-Lowry acids in Model 2? Okay, so make sure you're looking at the acids. There's an acid here, 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 and here. And what element is present? Well, look at that. It's hydrogen again. Okay, so there's a connection between Arrhenius acids and Bronsted-Lowry acids, is that they always have hydrogen. Okay, super important here. Hydrogen is key if we're talking about acids. All right, so all the Bronsted-Lowry acids have hydrogen in the formula. That's what number 1 was asking. Okay, so number 2 says, how can you tell from reaction 1, so let's focus on reaction 1, that HCl, hydrochloric acid, loses an H plus ion rather than a hydrogen atom? Remember, atoms are neutral. Ions have a charge when the reaction occurs. And it says, hint, look at the products. So I'm looking at HCl, and HCl is neutral. There's no charge up here. Okay? And if we look at our products, what happens when the Cl is by itself? It's negative, right? And it lost that hydrogen ion. So that hydrogen ion must have been balancing it out, and it must be positive. And some more evidence of that is, look, H2O turns into H3O plus. So it gains a hydrogen, but it also gains a positive charge, meaning that the hydrogen it gained was positive, right? So it didn't just gain it's not just H3O, it's H3O plus, okay? So water in this case is taking the hydrogen from HCl, becoming H3O, and it gets that little plus charge because it's actually taking an H plus ion and not just a hydrogen atom. Okay, so remember, we're talking about ions here. There's going to be charges involved. Okay. All right, number 3, again, pause the video, try it out. Okay, for each acid-base reaction in Model 2, so now we're going to look at all of them, describe the role of the Bronsted-Lowry acid in the hydrogen ion transfer that occurs. And notice, right, remember, hydrogen ion is just a proton. That's kind of interesting, right? Remember, hydrogen is just one proton. An atom is one proton and one electron. So if it's a hydrogen ion and it lost that electron, it's literally just a proton. But anyways, that's kind of beside the point here. So we want to describe the role of the Bronsted-Lowry acid in the transfer of that H plus ion that occurs. So let's look at reaction 1, because we just looked at that. So if this is the acid, right, what is it doing between here and here? Well, it's losing hydrogen, right? It's giving up or donating an H plus ion. Let's look at the other reactions. The acid here, HF, becomes just F. So it's also giving up hydrogen ion. In reaction 3, we have NH4 plus, and it becomes NH3. Again, it's giving up a hydrogen ion. And finally, you could probably guess, here's our acid, H2PO4 minus, a pretty, more complex acid, a little bit, right? And it becomes HPO4. So this also, the acid is giving up a hydrogen ion. So key point, a Bronsted-Lowry acid donates an H plus ion or a hydrogen ion, okay, in solution. So it's going to, a Bronsted-Lowry acid donates an H plus ion. That's key. Pause and write it down. All right. Okay. Now we're going to talk about the base, right? So again, pause, try yourself. Okay, so describe the role of the Bronsted-Lowry base in terms of the proton transfer or the hydrogen ion transfer that occurs. Okay, so if we look here, H2O is the base, it becomes H3O. So it's gaining or accepting the H plus ion. Okay, let's see if that pans out in the other ones. NH3 is the base. Oh, look at that. It becomes NH4. It gained a hydrogen, an H plus, right? It also has that plus charge. Here's the base, H2O again, and it becomes H3O. Look at that, gaining a hydrogen, H plus, or a proton. Same thing, remember. H plus ion, proton, same thing. And in reaction 4, our base is just this negative or this fluorine anion, right? And look at that, yep, HF, it gained a hydrogen. So, key point, a Bronsted-Lowry base is a proton acceptor or a hydrogen ion acceptor, okay? So in the Bronsted-Lowry model, the acids give up H plus or they donate H plus, and the bases accept H plus, right? Or they take the H plus. Okay, so acids give out the H plus or give it up, right? And the bases accept them. So we can think of a Bronsted-Lowry acid is a proton donor or an H plus donor, and a Bronsted-Lowry base is an H plus acceptor or a proton acceptor. Okay, key point. So now we've talked about 2 different ways we can classify acids and bases. Okay, remember Arrhenius acids have an H, right? Have a hydrogen ion, so it's very similar to Bronsted-Lowry, right? Bronsted-Lowry acids, they donate H plus ion in solution. An Arrhenius base is pretty different from a Bronsted-Lowry base, okay? So an Arrhenius base, the first one we talked about, has to have that OH minus, has to have that hydroxide anion at the end. But that's not true about Bronsted-Lowry bases. To be a Bronsted-Lowry base, all you have to do is be willing to accept a proton or be willing to accept an H plus ion, right? Notice NH4 is NH3 here is considered a base. It's not an Arrhenius base because there's no OH, but because it accepts an H plus ion and becomes NH4 plus, we consider it a Bronsted-Lowry base, okay? So that's the main difference there between the Arrhenius classification of bases and the Bronsted-Lowry classification of bases, all right? Okay, and one more question, right? Definitely try this one first, and I'm going to have to switch to my paper here. So it says, as you saw in Model 1, all Arrhenius bases in Model 1 have an OH minus ion, right, hydroxide ion, in their chemical formulas. We just talked about that. Write a balanced chemical reaction for the reaction of HCl, hydrochloric acid, with OH minus, a hydroxide ion, to illustrate that the hydroxide ion is also a Bronsted-Lowry base. All right, so check it out. I have it started here. We have, right, definitely an Arrhenius acid. It's got the H in front. Definitely an Arrhenius base. It literally has the only thing it needs to be that. It's an OH minus, right? That's how we know it's a base. Now we're going to show that this OH is also a Bronsted-Lowry base. So what's going to happen here? So remember, the acid donates the H+. So HCl is going to lose that H, and OH is going to accept it. Okay? So we could write this, right, as HOH, but that looks kind of weird, right? Let's count them up. How many H's? Oh, 2 and 1 O. Oh, we know what that is. H2O. All right, and what's left over? Well, if we combine these two things, only thing that's left over, oops, sorry, out of the screen there. Only thing that's left over is the chlorine. So Cl minus, okay? And yeah, both of these are aqueous, okay? Right, they're all of this stuff is happening in water, okay? All of this acid-base reactions are happening in water, okay? So we see here, remember the question was, we know that this is an Arrhenius base because it's an OH minus. It's a hydroxide ion. That's what defines Arrhenius bases. But we're also seeing that in this case, the Arrhenius base is accepting the H plus ion, so it's acting like a Bronsted-Lowry base as well, okay? So in this case, the OH minus ion classifies as both an Arrhenius base and a Bronsted-Lowry base. It's an Arrhenius base because it has the OH, and it's a Bronsted-Lowry base because in this reaction, it accepts an H plus ion to become H2O. All right? Cool. Yep, you know what time it is now. It is time to check your understanding. And yes, I gave you kind of a lot of questions, but they're multiple choice. All right? So pause the video here. Try out these 5 multiple choice, and then I will go through them. Okay. All right, so hopefully you paused. Let's go through these guys. Okay, so which species is an Arrhenius base? All right, so, and I tried to trick you here, okay? Remember, bases have to be ionic compounds. So if you pick D, you got fooled because this is a covalent compound. There are no metals here. Carbon, nonmetal, hydrogen, nonmetal, oxygen, nonmetal, hydrogen, nonmetal. It looks like a base because it has that OH. This is actually an alcohol. This is methanol, okay? So the answer is B because it has the OH and it's an ionic compound. Don't forget, that's why we talked about electrolytes, right? Electrolytes are ionic compounds. Acids and bases are, Arrhenius acids and bases are electrolytes, okay? So the answer is B, because of the OH, and because it's an ionic compound. All right, number 2, which substance is an Arrhenius acid? Okay, remember, Arrhenius acid, we're looking for the hydrogen in front, and there's only one, right? So that's going to be this guy, H2SO4, that is sulfuric acid right there. So see the H in front? When this dissolves in water, also remember, this is an ionic compound, right? SO4 is a polyatomic ion, okay? So when this dissolves in water, it's going to produce H plus ions and SO4 2 minus ions. Okay, so Arrhenius acid, you're looking for the H in front. So the answer here is A. All right, number 3. Which compound releases hydroxide, that's OH minus, ions in an aqueous solution? So again, we're looking for the base, right? We're looking for a base here. So this one could have fooled you too, because, it's definitely not 3. Right, because hydroxide is OH and there's no OH there. So we can get rid of 3 immediately. But look at this, OH, OH, OH. Which one is it? Remember, if it's going to produce hydroxide ions, if it's an Arrhenius base, it has to be an ionic compound. This is covalent. There are no metals there. This, also covalent, right? That was the other trick over here. So this is also covalent. So these are not bases. Number 4, look at that, same answer over here, so hopefully. Number 4 is an ionic compound, and it will produce hydroxide ions in an aqueous solution, or when it's put into water. Okay? Number 4, Identify a Bronsted-Lowry acid and a Bronsted-Lowry base in the reaction below. Okay, so remember, let's do the acid first. So a Bronsted-Lowry acid gives up or donates an hydrogen ion in the reaction. So we're looking for which thing over here has one less hydrogen over here. Well, NH3 becomes NH4. It's actually gaining a hydrogen. That's going to be the base, right? So look at this. HSO4 becomes SO4. This is the acid, okay, because it lost the hydrogen. I'm just going to put the A for acid. Okay, which means process of elimination, right? But let's, break it down. NH3, because it turns into NH4 and it's accepting that H plus ion, right? It's taking in that H plus ion. That makes NH3 a base. Okay? Now I'm going to push this a little bit further because remember, look at it, equilibrium. You guys remember this symbol, right? This is at equilibrium. So let's do the reverse reaction and then classify these as acids and bases. But now we're going backwards. So look, NH4 plus becomes NH3. It's losing or donating a hydrogen, so NH4 plus is an acid if we're going backwards. And then SO4 turns into HSO4, so going this direction, SO4 is accepting a hydrogen, therefore it's a base, okay? All right, and you'll notice in these reactions, Bronsted-Lowry, the acid always in the reverse reaction, it's always the opposite, right? So this is an acid going forward. It's going to be a base going backward, right? All right, number 5. One acid-base theory defines a base as, this is what I was talking about that Regents questions. This is the Regents question. So they will never say Bronsted-Lowry. They always say one acid-base theory. I don't know why. So a Bronsted-Lowry base is defined as it's definitely not 3 or 4 because there's no pluses, right? It's all about the ions, all right? So it's got to be one of these. So which is the one that, the base is the one that accepts the hydrogen ion, right? What's an H plus donor? What gives up the hydrogen, H plus ion? That's the acid. So this is an acid. An H plus acceptor is a base, and then these are nothing. These are just tricks because they don't have the plus signs. Okay, let me circle all these just so you can take a look at the whole screen. Rhenous acid, H in front. Here's the base again, hydroxide ions. Okay, all right. So that's the end of this lesson. Hopefully you can identify these different acids and bases depending on if you're talking about Arrhenius or Bronsted-Lowry. Feel free to review the video. I am going to go on to a challenge question here. But if you're good here, if you want to review this material now, try the homework, go right ahead, okay? So here's a challenge question. Write 2 balanced chemical equations, one where water acts as a Bronsted-Lowry acid, and one where water acts as a Bronsted-Lowry base, and explain your reasoning. Okay, so I'm going to go to the paper in a second here, but remember, what we want to do is we want water in one equation to give up a hydrogen, and we want water in the other equation to accept a hydrogen, okay? So let's see if we can figure out something about that here. So we have water, okay? Let's start off with acid, right? So if water is going to act like an acid, then it's going to have to give up a hydrogen. So whatever it combines with here, at the end of the day, it's going to give up a hydrogen and become OH minus. Right? That's the only way it can be an acid if it's giving up hydrogen. So, and then this could be what's going to combine with an H plus ion. We could pick lots of stuff. We got to pick a negative ion though. Let's say Cl minus. Why not? Right? And that's going to be, this is aqueous, right? It has to be dissolved for this to happen. It is also aqueous. Okay? So when the H combines with Cl, it's going to make HCl. All right? So in this case, right, water is acting like an acid because it's giving up a hydrogen ion. Okay, now let's do it where, I'll draw a line here, where water is acting like a base. So H2O is going to be our base. So we want the H2O to accept a hydrogen. That's what a Bronsted-Lowry base does. It accepts hydrogen ions. So H2O, we need an acid. We need something that's going to give up hydrogen. I'll keep it simple. Let's use HCl again. Okay. So what's going to happen is, in this reaction, okay, H2O is going to take that H and become H3O plus, right? Don't forget the plus because it's taking a hydrogen ion, not an atom. All right, and that's going to leave chlorine all by itself as a Cl minus ion. Okay, so that's a base, acid. This, we won't even look at that one. Okay. All right, so in this reaction, we have water acting like an acid because, remember, water, it can be either or. It depends on what it does when we're talking about Bronsted-Lowry. Bronsted-Lowry is all about, are you accepting a proton or H plus ion, or are you donating a proton or an H plus ion? Okay, so we can't just say, oh, water's an acid. No, because it could also be a base, or it could be neither, depending on, it could not even be an acid-base reaction. In this reaction, because it donates, because it loses that H plus to the chlorine, it's an acid. In this reaction, because it's gaining an H plus, it's a base. All right. Hopefully that illustrates the way we classify the Bronsted-Lowry acids and bases. All right, that's going to be it for today. I will see you guys on Monday if you're watching this on Friday. All right.